Okay, so that was quite technical, and what we're going to do now is think a bit about how to visualize data. That's going to lead on to in chapter 4. So this chapter 3 is about sort of how to visualize things. That visualizing is going to be useful when we get on to chapter 4 and we visualize by hand some things about the multivariate normal, right? Because what you'll notice is I like to write down, so your data's like that, your data's like that. Well, what does that mean, right? You will understand what it means for your data to be like that and like that after the next 2 chapters, and that's just very helpful for how to think about things. Okay, but statistics is about more than just the mathematical theory, right? As you'll probably have noticed, it's always in the news. What are the actual numbers for something? So it's a profession with associated responsibilities in society. The Royal Statistical Society, and I think most national societies, publish sort of codes of conduct, and so it says you should act in the public interest, do what your employers and clients say, fulfill your obligations, and be professional and so on. But the bit that I like to pull out, particularly here, is it said you should ensure that any statistical analysis attributed to you by an employer, client or colleague is amplified, if necessary, by a description of the way the data was selected, the way any apparently erroneous data were corrected or rejected. So explicit statements will generally be needed about the assumptions made when selecting a method of analysis and any consequences of the approach. So views or opinions based on general knowledge or belief should be clearly distinguished from views or opinions derived from the statistical analysis. Okay, so a lot of this stuff about the assumptions made, that's why we're doing the theory, right? There are assumptions made and you should know what they are, and when they might not apply, okay? But also you need to be able to describe the data, right? You can't just trust every Excel file you're given, right? You need to have a look at it, and I'll say why. And that's what exploratory data analysis is. So it's about getting an intuitive understanding of the data, usually before any formal statistical procedure or analysis is performed, right? So as such, different people will find different techniques useful, and different data and research questions will require different approaches to EDA, okay? So it can be used for various things, examples being investigating the most important properties of and relationships between variables in the data set, checking data sets against each other and against models, or informing which formal analysis to use. So it will turn out that the techniques met will be useful for data visualization, also following a statistical analysis, right? So has anyone seen this before, Anscombe's quartet? So this is a very, very famous example by Anscombe, and it's 4 simulated data sets, where each one would have the same regression line. In our case, the regression line is the correlation, the correlation between, so it's the off diagonal of S, if we're thinking about this being variable x1, this being variable x2. But the way in which they depend on each other is diverse. So it's the ways in which things can be non-independent is very different from the ways in which they can depend on each other. So here you've got the kind of nice picture that we're normally thinking about when we say things are correlated. There's some spread in each one, right? But here you've got a kind of non-linear, very strong dependence, very low noise, but the line is just the wrong way to describe this relationship. Here you've got things that look like they're on a different line, but something's I hesitate to say outlier, because outlier is not terribly well defined, right? But you can see that there's one point that is out of the trend of the other ones. And here you've got lots of noisy points here and one point here, and that's the. So describing all of these using correlation alone is probably wrong, right? In this case, yes, but in the other cases, there's something else going on. Now, Anscombe somehow managed to do this, by hand or with an old computer from the 70s, right? Now computers are fast. You can do this quite fun thing. And so there's this nice paper called the Datasaurus Dozen, where they started with a picture of a dinosaur, and the dinosaur had they said that's got an X and a Y, yeah, and it's got a certain standard deviation, a certain correlation, and they created these 12 other data sets that had the same statistics as the dinosaur, right? So a cloud, 2 lines, circles, these 9 points, right? All of these data sets, you can download it from the paper, they all have the same properties as the dinosaur, right? So you can go even further. This is just going even further than Anscombe with modern computers. More interestingly, the study A Hypothesis is a Liability. What they did is they gave students 2 data sets and said, I want you to look at, correlation between these 2 things, right, in the data set. And if you plot the data, you see there's a gorilla, right? But not everyone did, okay? And the ones that were told, I'll just test this hypothesis, never plotted and never saw the gorilla, right? Or they were less likely to discover the gorilla. So I don't know if you know the famous one with people playing basketball and you're asked to it's a psychology experiment where students are asked to count the number of times a basketball's passed and a gorilla walks across, right? And you don't notice the gorilla. Now that doesn't work anymore because everyone's looking for the gorilla now, right? People know about it. But this was like a paper where they did the same thing. They said that you should sometimes just look at the data, right, without thinking on what you're about to do with it at all, and just say, visualize every bit of the data, right? And that doesn't guard against all problems, but it guards against the ones that would be really, really embarrassing because you didn't visualize the data. Yeah. Okay. So that's the in applied stats people will go on about this a bit more, always visualize your data, but it's equally important in more theoretical stats as well, right? Because you're going to go on and do. Interestingly, this is a 2x2 table, which we do in chapter 9. Okay. So a nice source of real data sets is the University of California Irvine Machine Learning Repository. So I got this data set on automobile miles per gallon. Remind me to put the R code up actually once we've met this, but you can get these data from Blackboard and play with them in R. What do these numbers mean, right? So this is the code I'm going to show you here is in R. So I'm going to read a table. So this is using base R, right? These days almost everyone uses tidyverse, so I'm kind of wondering about whether I should anyway, what am I saying? I think this, so some of this is tidyverse, some of this is basic R, right? So just be aware that R is, lots of people are using tidyverse these days, right? It looks quite different from standard R. Okay, so what do the numbers mean? Well, there's a metadata file when you download it from this website. There's what's called a metadata file which tells you what the attributes are and whether they're continuous, multi-valued, discrete, and so on, right? So if you look, it says that first one, V1, is miles per gallon, which is continuous. Yeah, cylinders is a number, right? So let's just check quickly. Do you remember, is cylinders integer, ordinal, or nominal? Do you remember the 3 kinds of integer data, is it? It's an integer, right? It's a number. Yeah. So cylinders is a number of cylinders. 8 cylinders is twice as many as 4. Yeah. That's the same for model year. Origin is whether it's European, Japanese, whatever. So is that, what's that? Is that ordinal, nominal, or that's nominal, right? Because it's like they've coded Japanese as 3 and European as 2 or whatever. Yeah. And I think year is continuous because that's the type. That's like a calendar year when it came out, right? So 1980 is 2 years after 1978. Okay. This is quite an old data set, it's from the 80s, right? So the first thing I do is I rename. I'm renaming these things that came as like V1 to VA using the metadata. Yeah. Okay, and then there's this nice style rule that David Spiegelhalter gives. Okay, and I think this is a good place to start when you're doing an analysis. So your sort of 4-star is numbers you can believe, for example, official stats or controlled laboratory experiments. 3 is numbers that are reasonably accurate, so like a well-conducted survey, field measurement. Less well-controlled experiments. 2 you said could be out by a long way. Yeah, and that could either be because the experiment was done badly or the survey was done badly, or the system itself could just be very, very high noise. So in astrophysics, people think they're doing quite well if they've measured. So to give an example, I mean, physics has some good examples. I think the most accurate measurement of anything is something with the hydrogen atom that is like more than 20 significant figures accurate, right? But I think if you get the Hubble constant right to within like 3 orders of magnitude or something, you think you're doing within an order of magnitude, you think you're doing quite well, right? So measuring the whole universe turns out to be quite hard, but things that you can control a lot on a tabletop are very highly accurate. Then 1 is numbers that are unreliable, so if it's very biased or biased equipment, and 0 is just made up. 93% of statistics are made up on the spot, right? It's and the point is that if you're in the kind of 1-0 regime, you just shouldn't be doing stats on the data, right? You shouldn't dignify a completely pointless, made up or really very biased data set with a really nice analysis, okay? The point where you kick in is where there is a lot of inherent noise, right? And so it's a worthwhile attempt to measure something. And actually, normally, oddly, once you get to 4, you don't often need stats because the measurement has been so good. You don't need to do any statistics. They have measured the number, right? So statistics comes in normally around this regime here, right? 2 to 4. And so how would we classify this data before we jump at it? Well, I think it's 3 or 4 star. It's manufacturers' data on automobiles that it's going to have it. If they say a model has 8 cylinders, you can open up the bonnet and see it has 8 cylinders, right? So there'll be some slight errors with it, but it's that I think is going to be high quality data, so it's fine to look at, right? So what I'm going to do is just, like with everything, revisit the univariate case and then do the multivariate case. So in univariate exploratory data analysis, we think of the data as a length n vector x. That's instead of our data matrix. And we then calculate quantities of interest like moments. So if we take the third column, so we said that's displacement, right, which means engine size, yeah. So if we take the third column, we said that each column of the multivariate data matrix is a univariate data set. So that has a mean. So the mean displacement is 2 litre, is just under 2 litres. Yeah. The variance is 10,000, right? And there's a bit under 400 cars, right, in the car models in the data set. Okay. So let's look at how to plot this. So just displacement. The units used are slightly old-fashioned, but this is like 1 litre, 2 litre, 3 litre, 4 litre, right? Engines. Bearing in mind these are cars from the 70s and 80s. So in a box plot, you show the percentiles of the data. This is what's called a highly lossy method of displaying data, right? So lossy versus lossless. If something is lossless, in theory, you can reproduce it. It contains all the information in the data set. Right, if you really zoomed in on the plot. If it's lossy, then you can't reproduce the data set. So there's multiple data sets that could map onto that visualization. Okay, so ggplot2 is a really good way of plotting, so I'm going to do almost everything in ggplot2. That's part of the tidyverse. This is how ggplot looks. You ggplot it, you have an ace, which is an aesthetic, and then you add to it different plots, box plot, and so GG stands for grammar of graphics. So the the people who wrote it have an idea about how you should specify graphics, right? And that causes them to write it like this, right? But it produces very, very nice plots. Okay. So here's a risk of lossy visualization. This is from the Datasaurus paper, and all of these A to F, they all have the same box plot, right? All of these, but they're very, very, very different data sets, as you can see. Yeah. So the same thing they used to like move the dinosaur onto the square and everything, they could use to move the data. The same algorithm, it's called simulated annealing. They could use to produce these data sets that were very different. Okay, so there's a risk of lossy visualization. That's not to say never do it. I don't think it's as simple as saying never do it, because sometimes you need to lose information because you've got to have so much. If you've got like 50 box plots, right? 50 plots that look like this is too much. So as long as you've sort of checked that each box plot isn't misleading you, right? 50 box plots is fine, because that's a lot of information. Yeah. So you need to be a bit pragmatic, but this is just about saying check, right? Get in the habit of checking. Okay. So the jitter plot is a lossless visualization technique. Yeah. And what you do is we'll see a scatter plot later, but you plot everything as a dot. But the issue is if you plot everything as a dot, lots of things are on top of each other, because lots of things are pretty much exactly a 1 litre engine. So what you do is add a random, you raise each point to a random height, yeah? So I pick uniformly at random between, I think here I pick uniformly at random, not quite between 0 and 1, because I'm never quite getting there. And what you see is something that looks like this, and you can see that these data are indeed a bit like these ones on the left, a bit clumped up, right? And that's why I pick displacement or engine size, because you see, if you are ever unfortunate enough to be buying a car, they'll make a big deal of, oh yeah, it's a 1 litre engine, 2 litre engine, right? They don't sell it's a 2.347 litre engine. People tend to snap the engine size to whole numbers of litres, right? So 1, 2, 3, 4 litre engine is common, and then you've got your 3.5, you know, so you've got your 2.5, 3.5, right? But and then you've got some distribution around 1, right? But it's that manufacturers don't just uniformly pick an engine size. They do it. There's some elements of that, and in between the box plot and the jitter plot, possibly in a sweet spot, is the histogram, yeah, where you plot a height of a bar. The height of the bar is how many observations are in that region. So you lose some information, but you keep a lot of the structure, and then in a way you can interpret the histogram as an estimate of population density at each point. So this would be a piecewise, each of these bar heights could be a piecewise constant estimate of population density in that region. Does that make sense? So we know that the population random, so we think that each, I'm going to explain what I mean by that. So each so remember we're saying that x is a random variable, and we've got x in the univariate case is our data, and each xi is an IID copy of x, yeah, and we think that means that there's a population density function fx, yeah, of this x, right? And so what we're doing when you do a histogram is you're saying this is approximately, yeah, you're saying it's approximately this function, yeah. You're saying it's so histogram as a piecewise constant estimate of f, yeah. And that's how you can kind of optimize what the bin widths of the histogram are. So you can write it like this, and that makes clear in what sense the histogram's an estimate of the population density. Okay, how you set the bins strongly affects the result, so you can try to quantify uncertainty in an estimator f hat, right, and so on. So we're not. They do. If you're on the MSc, they do this in. I'm pretty sure they do this in statistical inference, right? Estimating piecewise constant estimation. But that's just to say that the other visualization we'll look at that's sort of lossy, but not a nice thing in between, is that so your actual sample is lots of points. Is some points along here, with a few points here, and then loads and loads of points here, which are all on top of each other, and then less. Yeah. So that's why you can't just plot them without jittering them, because they'll all be on top of each other. But what you do in the kernel density is, for each point, you put a little normal distribution around it, and then you sum up all those normals you sum up the height of all those little normals, and because you've got more normals here, you get a higher curve. Yeah, that's called kernel density estimation. I say little normals, can be a general kernel K, calligraphic K here, but the normal is the most popular choice, right? But you can do top hat kernels and so on, right? This is also lossy, but as for histograms, it's based on an estimator of the complete PDF rather than the box plot, which just visualizes summary statistics. So here's what you get with R. Again, you can try to optimize this parameter W of the kernel in the same way you can try to optimize the bins B. Yeah. And what you see is again, you see what is there in the data, which is a peak at 100 and other peaks at other points, but I mean you can see that actually it probably in this case slightly over smooths the data. Yeah, the default behaviour of GG plot is slightly over smoothing, so I would say here that this is much more useful, right? Because although this follows it doesn't quite get down to zero, because what you've done is you've assumed that this point here has some width that carries over, right? So it's a bit slower at saying, oh yes, there's a zero here, because you've got some points here that are still like moving in, right? And that can be a good or a bad thing depending on the nature of the data, right? That if you think that it's unlikely there are going to be true zeros, then the kernel density helps. That smoothing property is a good one, right? If you think it's quite likely there are real ones, then a piecewise constant is better. And this comes in a lot with like classification, machine learning, whatever do you want. So piecewise, so the random forest that will be your decision trees are kind of piecewise constant type approach, right? And other like discriminants are more about, let's assume that everything's a bit like a normal. Yeah, it's not quite as simple as that, but these are also like philosophies of what you're trying to do with the data. Then the final univariate one that we'll think about is the empirical cumulative distribution function. So this is, you probably met this, it's the cumulative distribution function of the data. You can define a multivariate version of this, but you don't normally, right? But I think even with multivariate data, it can be good to plot every univariate ECDF. And it's particularly useful because the survival function on a log scale does tell you a lot about the extreme values, right, in the data set, because the extreme values can really bias things. So I just advocate this as like just a bit of statistical practice. Plotting ECDFs can be useful, particularly plotting 1 minus the ECDF on the log scale, because you see what the biggest observations are, right? So these are all univariate ways of plotting things that you may or may not have met, and the basic idea of why we try to do EDA. So what we will do on Thursday is go through the multivariate ones. I'll tell you then as well what kind of problems in the exam you'd be expected to solve on the basis of this EDA, because it's one of the learning outcomes. And then we'll start seeing how things like the kernel plot or whatever, how some of these plots we can do them by hand. How we can do them by hand for some distributions, right? That's what's coming after the EDA. So any questions on that bit that we've done?